you were just at the previous Trailblazer session, welcome back. And if this is your first session with the Trailblazer, welcome, welcome. My name is Christopher Little, I'm Associate Director of Business Experience and Student Engagement. And we're so happy that you're here at NYU and hope that you've been having a great time here at Weekend on the Square. Has it been a good time? Yes? Absolutely. Good, good, good. That makes me happy. All right, so we have another Trailblazer today, one of our wonderful faculty members here to talk to you a lot about an area of topic that they are truly an expert in and quite knowledgeable within, and give you a bit of a glimpse of what you can expect at NYU once you jump into one of the classrooms, okay? So we have up next Nikolay Kukushkin, and he is the Clinical Associate Professor of Life Science and Liberal Studies and a Research Fellow at the Center for Neuroscience here at NYU. He holds a Doctor of Philosophy and Biochemistry from the University of Oxford and a Bachelor's of Science in Biology from St. Petersburg State University. His research deals with the role of time patterns in memory formation. His academic work has been published in Nature Communications, Nature Medicine, Neuron, and PNAS, among others. He's the author of a best-selling award-winning book, One Hand Clapping, Unraveling the Mystery of the Human Mind, which deals with the origins of human consciousness. The book will be published in English in 2025, so make sure you all get a copy and then get it signed, all right? So if we can all put our hands together for Nikolay and see what he has to say.
So before I talk to you about science, I want to talk about science fiction. So I don't know if you've seen the show Black Mirror. If you haven't, you should watch it. It's great about speculative ideas about science, specifically about the brain. There's this one episode called Crocodile. It revolves around two women. It's the protagonist. This is an insurance agent who investigates an episode. And she uses this device that she places on the witness's forehead. And this device projects the memory of the witness onto this little TV screen. And she watches her memory, the protagonist's memory, and basically she sees something that she's not supposed to see. And drama ensues. I won't tell you more than that, you go watch it. What I want to talk about is this idea that if we just had the right technology, of course we don't have it, it's science fiction, but if we just had the right device, we would be able to extract the memory from someone's brain, project it into another device, view it in another medium, maybe even in another person. It's not a new idea, it's not new. Here's a page from a 1902 book about hypnotism. So this would of course be considered pseudoscience today, but notice it's basically the same idea. Here's a person observing something, a cow, and here's another person connecting to the first one through hypnotism and viewing the memory of the first person through their own eyes. It's the same idea. If you have the right powers, the right technology, there is a way for you to visualize someone's memory, to copy someone's memory into another device, into another brain. And basically what I'm about to tell you is that that's not how memory works, or rather that's not what memory is. It's just not the right way to think about memory. So let me give you a few examples that hopefully will lead us to this idea. So first of all, here's my credit card number. Okay, let's review what just happened. So the screen produces some photons. They produce in a particular pattern. They hit your eye, they hit your retina. They get converted in your retina into a specific pattern of photoreceptors that are activated, that starts pinging your brain through this Morse code of signals. They start circulating through your brain, and as they do, they widen the channels where the electrical signals travel. That is the memory. It is easier for you to recall it because the channels of communication between the neurons in your brain have been widened. By the way, what is my credit card number? What do you remember? Just say it out loud. What part of it do you remember? 484. Everybody remembers 488, right? So 888 is easy to remember. It's a pattern. If you're like most people, maybe you would remember 9. Maybe you'd remember a little bit of this. Maybe you'd remember the ending. But very few people remember this middle part. Just in case some of you have photographic memories, not exactly my credit card number. Occasionally, some of my students are very good at remembering things like this. But this already tells us, very simple, but it already tells you that your memory is not a camera. It's not, we like to believe that it is a camera, but it is not. If you had a camera instead of your eyes, then it wouldn't make any difference. Is the beginning of the sequence? Is this the end of the sequence? Well, you take a photo of that credit card number, and then you can access it and do whatever part you want. But that's not how it works. We memorize beginnings better than middles. It's called the primacy effect. There's the primacy effect and the recency effect. So in this case, it's taken from a paper where people were memorizing words in a sequence. It doesn't matter what kind of sequence it is, words or numbers or pictures. You remember the beginning of the sequence best because it's first, that's primacy. You remember the end of the sequence almost as good because it's the most recent thing that you've read. In the middle, sort of falls through. Very simple effect, but already tells you that our memory is subjective. It's not exactly like a camera. Let's look at some more things. Which one is the correct penny? Anybody with a fathom a guess? Anyone? Just say it out loud. Go ahead. B. Anyone else? B. I. F. Go ahead. E. No. A. I forget every time. Honestly, I show this every semester. I have to look at this every time. But for the first time this semester, I had one student who immediately said A. And I was like, wow, this has never happened before. And she said, well, I worked all summer at the register. But that is interesting because that tells you that depending on how relevant something is to your life, you can remember it better or worse. It's not about how many times you've seen it. We've all seen those pennies thousands of times. So it's not just about taking a photo of an item repeatedly over and over. You know, it has to be relevant to your life in some way. Then you remember it. And what is relevant to your life is really subjective. It depends on all your past history. It depends on who you are. It depends on your other memories, on your language, on all those other things. So again, not a camera, not a video file, not a photo, not an audio file. Now this one might be a little bit easier. Which one's the correct stop sign? Go ahead. 3. This one? Yeah. Not quite, but close. This one, yeah, there you go. So usually this one would be a little bit easier than the pennies, and I would ask students, do you drive? And invariably, the person who guesses, do you drive? Yeah. Yes. Invariably, the person who guesses it is the one who's driving. You have more experiences with this sign. You've spent more time thinking about it, and you remember it better. So memory is subjective. Depending on who you are, you remember different things differently. And we all are confident in our memories. We don't think that we remember some things better and some things worse. So we all have these vivid memories, sometimes from a distant time in the past. They're called flashbulb memories. And this has been studied in association with big events like 9/11, for example. We all have, well, if you've lived during that time, many of you guys haven't, but if you're like me and your parents, well, you probably remember what you've been doing during 9/11. And so some researchers went out into the field immediately, a day after 9/11, and they collected interviews from people. Details, what have you been doing, how did you feel, what did you experience? And then they returned to the same people a week later, about a month later, and almost a year later, and they tallied how many details in their recollection were consistent with that original fresh memory and how many were inconsistent. And as you can see here, the consistent details go down, almost a third of them goes away, and just under a year, inconsistent details go up. And it's the same for flashbulb memories and everyday memories. We forget things all the time, and that doesn't bother us, but we have these memories that we're very confident in. We remain confident in them, despite evidence that they deteriorate over time. We replace details with confabulated details. We fabricate parts of our memories without even noticing it. So what does this tell us about witness testimony? What does this tell us about that Black Mirror episode? If somebody connected to your brain and extracted a flashbulb memory from it, would they be extracting the original one or the one that's a year later? Well, it really depends. It depends on where that memory is in the moment, what you've been doing with it all this time, how you've modified it over a period of time. Just the fact that you would be able to visualize it doesn't make it real, doesn't make it reflect reality in any better way. There's a famous study that has to do with witness testimony as well and with false memories, which is what I just described to you with the 9/11 example. This is a Loftus and Palmer study where this has been done in the 70s, a bit of a retro video, but all the people in this study are experiencing the same video, controlled conditions, the same room, same screen, same experience. Let's experience it. Okay, so then the people, the participants of the study are distracted, they're given some other tasks, they're being walked around, and then eventually they're given a questionnaire. They're given a sheet of paper to fill in, and among the questions is a question about how fast were the cars going when they, and then different people get a different version of the question. Some people are asked about how fast were they going when they contacted each other, others, how fast were they going when they smashed each other, and I'm sure you can predict the results, depending on which word you use. Contacted, hit, bumped, collided, and smashed. The average speed reported by these people scales proportionally. So these are large numbers of people. It should be the same on average, but it's not. Depending on how you ask the question, not even the content of the memory, not from which angle you watch it. Now that is all the same. The only difference is how you ask the question. And so, well, again, what does that tell us about witness testimony? What does this tell us about the reliability of our memory? Our memory is something that is specific to us. It is specific to the moment when we produce that memory and to everything that happens later on. So let's do a little experiment here. I got to admit that this is the first time I'm doing this in a big room like this. It works in the classroom. We'll see if it works here with you guys. If it doesn't, well, you'll forgive me. So what I will do now is I'll turn this on. I want you to look in the middle of the screen, and it will flash numbers and pictures. Picture number, picture number. There'll be a lot of them. Try to memorize as many as you can. It will be hard. You're going to move pretty quickly, but I want you to do your best at memorizing them. And then I'll ask you, here's a picture, what number went with it. You remember, do your best to just say it out loud, and we'll see what the audience response is, okay? So get ready, stay in the middle of the screen, let's go. For those signals to clear up in your brain, for neurotransmitters to clear between synapses, for ion channels to get installed into the membranes of your neurons, and that is what's happening right now. Okay.
65.
65, right? Okay, it worked. So everybody remembers the puppy a lot better, right? It took me a while to pick a good image. I used a kitten in a sock for a while, and that wasn't nearly as effective as a puppy in a cup. I don't know what that tells us about the science, but my point here is what you memorize, even though the time that you spent looking at those pictures is exactly the same, but, well, there was one picture that stood out among all the boring ones. Tools are boring. Most people don't care about tools, which is why neuroscientists love them so much. It's a neutral stimulus that you can present to people without any emotional response. But, well, we like puppies, we like cute images, and so in that moment where you saw the image, and 65, you got this little jolt of dopamine in your brain. It physically sprayed over some neurons in your hippocampus, strengthening the connections between neurons that were sending signals into that part of your brain at the same time, and so you remembered this association better, and so we got a more consistent response from the audience. That's exactly what you expect. But think about every moment in your life when you got that little jolt of dopamine. How individualized is that pattern? And how different would your recollection be compared to anybody else looking at the same scene in the same way as you did? So everything that I'm telling you, the conclusion from what I'm telling you is that memory is personal. We like to think of it as a standalone object that you can remove from your brain, place somewhere else, copy from one person to another, but that's not what memory is. Memory is how your brain changes in response to your experience. It's not someone else's, it is yours, and it will never be someone else's. So why is it that we can copy a memory between computers, but we can't copy memory between brains? Well, because computers consist of the same parts. They're manufactured in the factory according to the same instructions. Their hardware is the same, but this is our hardware. Well, it's a very idealized cartoon. Everything is a lot messier in the reality of the brain. But basically, our brain is a network of these neurons that connect to each other using synapses. And everything we experience passes through this network of neurons according to how they are wired with each other, in what configurations they're connected with each other, what connections are stronger, what connections are weaker. So you can think of the entire brain as this machine that converts our senses, what we input through our eyes, through our ears, our skin, our nose, our tongue, all of our sense organs. Then those signals pass through the synapses of the brain, bounce around like a pinball through all the connections of neurons, and eventually they output behavior, what we do, how we move, where we go, what we say. Every action you take is behavior, and your brain is what converts one into another. So what is experience? You can think of experience as the flow, the routing of this flow between senses and output, between input and output, between senses and behavior. And memory is how the routing of the flow changes. As those signals flow through the brain, they automatically modify the channels through which they flow, just like water flowing down a rock that carves its own path. In the same way, electrical signals that pass through our brain carve their own paths, and that carving is the memory. It is unique, it is different in each individual. There is no synapse from which I can move my memory to your memory because we have different synapses. So why can you copy a memory from one computer to another? Because they are the same in their hardware. You could think of two different computers as having two distinct information pieces, distinct content, but then you can copy this content from one computer to another because the hardware is the same, and then you can make these two computers have the same content as well. But how do you do that with a brain if the configuration of the hardware is distinct in every individual? There's simply nowhere that you can copy this content from one brain to another, even if you had the right technology. So memory is personal. It is personal for our brain. It is how our brains modify themselves in relationship, in accordance to our experience. And what our research shows is that not only brains modify themselves depending on our experience, but also our bodies modify themselves. Even generic cells of our body, such as kidney cells, have their own memories that apparently work in the same way as memories formed by neurons. Just as neurons modify their synapses when they receive signals from other neurons, other cells of our body also modify themselves when they receive signals from the environment, from other cells. That might mean nutrients passing through them. It might mean the flow of liquids or salts or temperature or anything else that cells of our body might be experiencing. What we now understand is that all cells of our body are attuned to find patterns of experience, that they can detect differences in what we do to them on the scale of minutes, which is not something that we expected before. So how did we get to this? How do we work with these cells? We grow them in petri dishes, and here's me getting experience with those cells. We add chemicals that imitate signals from other cells, we perfuse them, we grow these petri dishes, and we can control the timing during which we deliver those experiences to those cells. So what we know about a typical memory, this could be a human, an animal, really anybody who can form a memory. Memory follows the so-called masked-spaced effect. So if you have the same amount of training, and this could be you studying for an exam, or it could be a rat studying in a maze, if you train the animal or the human for the same amount of time, you produce an inferior memory if you cram all the training together. That's called masked training. Then, if you space it with intervals in between, you produce a stronger memory with spaced training than with mass training. So that is well known since the 1800s about basically every form of memory that we know, but nobody's so far seen that outside the brain. What we have shown in our research is that generic cells, non-brain cells, even kidney cells, also follow this masked-spaced effect. If you deliver chemicals to those cells that imitate signals from other cells, and you can control the timing, you can do it in a masked way, you can do it in a spaced way. Here we have 3-minute pulses separated by 10 minutes. Here we have a single quadruple 12-minute pulse. But in this case, you produce a weak response. These cells activate a special memory gene that we monitor. And in this case, you produce a strong response. So that is evidence that the cells form memories in the same way, according to the same mechanism, using the same tools as brain cells do. So we now understand that not just brains, but our entire body is responsive to our experience. And what does that mean for our everyday life? we don't know yet. We don't know exactly what kinds of patterns does our stomach register or what our kidneys are looking for. We know that this is possible, but we don't yet know how we might harness it for health in disease. This is something that is a new direction that our lab is excited to study. So I would like to thank my lab. These are my colleagues, Robert Cardi and Desmond Tabassa, my mentor, Tom Carew. There's also Anastasia Susha, an undergraduate student who was helping us with this research. Tom Carew is my boss. Everything I know about neuroscience I know from him. He's not usually this grumpy. He usually looks a little more pleasant. Also former Dean of College of Arts and Sciences, towering figure in neuroscience. So I'm thankful to all these people and to you if you like the talk today. My book is coming out in October. You can pre-order it now. Follow me on social media, and I'll see you on the square. Thank you.
Trailblazer. I think it's just evidence how powerful and just intelligent and sort of experts in a lot of different ways a lot of our NYU faculty are. So I hope you really enjoy. It's really fun and engaging presentation. Just a reminder before you all leave, again, we have a lot of things happening today and weekend on the square, so don't forget to go to the resource hub. If you can, take a tour if you have enough time, or to see a residence hall. We also have the Meet NYU mingle happening at 3 o'clock in Paulson, so we definitely want to see you there. So there's going to be some music, some robots, some good times. Just make sure you come, all right? And then don't forget, if you have any questions about anything NYU, beyond this point, we have a lot of staff and students around that can support you and engage you and make sure you have all the answers to the questions, all right? Thank y'all for coming here today, and we will see you around the campus today, tomorrow, and let's go ahead and say it in the fall.